All right. Welcome back, everyone, and thank you, Casey, for the previous talk. Amazing detail and amazing amount of research you must have done on that. This talk is hopefully going to be a little bit shorter, so we get lunch. So Sam reached out to me a couple of weeks ago and asked if I wanted to present something, and I came to think about this work I did about half a year ago on optimizing and parallelizing the constraint solver for our upcoming game. And as it turned out, this talk isn't going to be that much about the constraint solver or how to parallelize it. It actually is going to be more about the low latency thread pools and job system that I had to write to make it all run efficiently on modern hardware. But I hope you'll enjoy it anyway. You're going to see some physics movies at least. So just some background on me. I'm Dennis Gustafsson, and I am the original creator of the game Teardown, which is a voxel sandbox heist game that came out in 2020. I was also the only programmer on the project up until the initial release, and now we're a bit more. It features a custom software voxel ray tracing engine, which is pretty special, and also a custom physics engine that operates and does collision detection directly on voxel volumes, and a bunch of other stuff. If you haven't played it, ask me afterwards. I have a bunch of codes to give out if you want to try. So for the last year and a half, I haven't actually been involved in the further development of Teardown, even though the development continues. I've been making prototypes and started to implement a new engine for an upcoming game. And that's the one I'm gonna talk about today. So it's an engine that is relatively similar to Teardown. We wanted to take all the things we learned from Teardown and remove a lot of limitations and restrictions on the old engine, and see how far we can push it, basically. So one of the things we did was to we rewrote the graphics to use parts of the hardware ray tracing pipeline. It's still tracing voxels at the very lowest end. But by doing that, we could up the number of dynamic objects dramatically, because the old engine worked in conjunction with the CPU and the GPU. Because I was using OpenGL at the time, because I didn't know better. So I didn't have access to the hardware ray tracing. But now that we do it in Vulkan. I also had to rewrite the physics to feed this new graphics engine with lots more objects. And doing that, most of the work went into making everything run very parallel, because in this time that passed since the development of Teardown, desktop PCs and gaming PCs got a lot more threads. So that's really the key to getting more performance. So a little background on physics engines, even though it's not really the topic of this talk, could be good to know an overview at least of how they work. So you have a bunch of objects, and what you typically do is split the workload up into two phases. So you have first phase is collision detection, which means you're gonna look for pairs of objects that are close or overlapping and figure out some kind of contact points where they collide. And that part is ridiculously parallel. It has no data dependency. You can just split up all the pairs and do them parallel. There are no locks or anything you need to do that. So very easy. The other part, when you have this list of constraints, is the constraint solver. And that takes the dynamic state, which is the velocity and angular velocity of all the bodies, and it tries to advance time into the next dynamic state for each body while taking all these constraints into consideration. And the way Teardown does that, and almost every game out there right now, is to do that using a method called projected Gauss-Seidel, or sequential impulse, also another name for the same thing. And the way it works is very simple, actually. You just sequentially satisfy all these constraints. It's like a relaxation method. So you satisfy the first one, compute an impulse, apply it to body A and B, and then you progress to the next one and do the same thing, which applies impulse to B and C, and then the third one and the fourth one. And as you can imagine, this has to be done in sequence, and that's what makes it absolutely terrible to parallelize, because you have to complete the first thing before you can progress to the next, because you want the result from the impulse up here to be applied to B before you measure how much of an impulse you want to apply on the second contact. And that makes a huge difference in terms of convergence for the solver if you do it that way. So you go through all these, and as you can imagine, when you solve the first one, it's going to be solved perfectly, but already when you solve the second one, it's going to like disturb the solution on the first one. So now it's not going to be satisfied anymore. So when you've done all the contacts, you're going to have to go back and do it one more time, and then one more time, and one more time, and you do it like iteratively. And a typical number that games use is like 4, 5, 6, 7, 8 times in that range. Teardown uses 8. This new engine uses 6. And intuitively very hard to parallelize because of this sequential thing. So what Teardown does, and also most other games or physics engines, is to instead of trying to split the way we solve constraints, is to split objects in the world. So if we have a bunch of objects over there and a bunch of objects here and they don't touch, those can be solved as separate simulation islands on multiple threads. And finding those groups is also relatively cheap. I included a little screenshot here of what it might look like, and also a profiling graph down here. We're going to be looking at these quite a lot throughout the talk. So if you haven't seen them, it's like a frame profiler or like a timeline profiler. Time moves from left to right. Up here you see the main thread, what it's doing in a hierarchical way. And down here I included, these are the worker threads. So it's using a thread pool. Workers are told by the main thread to start high-level jobs, and then all the threads, when they're occupied, they show in green, and when they're waiting for something, they show in black. So each line here should be thought of as a worker thread, and then it also, time progresses, this thread here does something here, then it waits a little bit, and then it works, and then it waits, and it works, and it's all told by the main thread when to do that. And if we look at how it would be split up, we can just intuitively see these simulation islands here. They would all generate tasks that go into the job system. And as long as we have enough of these islands and they're roughly the same size, this is a pretty good way to do it. But unfortunately, in Teardown and quite a lot of games, it looks more like this. You have maybe some small islands here, but if the player is given the chance and a lot of tools, they will do that. And that's going to be one single island, and it's going to take a long, long time to solve that on one single thread, while the rest of the machine is basically doing nothing, except for waiting on that. So this has been ever since initial release of Teardown, this has been the biggest bottleneck for the game. And this is a common problem, not just for Teardown, but for any physics engine. So another guy who thought about this a lot is Aaron Cotto, author of Box2D, who most of you probably already are familiar with. He worked on this problem last year and released his findings in Box2D version 3 that came out a bit more than a year ago. And he also wrote about this on his blog. And Aaron is a really smart guy and really nice guy, so I just want to give him the credit for this. I'm just using the same thing. So if you want to look up the details, look at his blog, it's amazing. And I just want to quickly describe how it works. It's a technique called graph coloring, and it's a way to split up these large islands into chunks that can be solved in parallel. And it's also a very intuitive method. You go over all the contact points, and you sweep over all of them, and you mark the ones that actually can be solved in parallel. And in order to be solved in parallel, they cannot affect the same bodies. But there's going to be a lot of constraints that affect different bodies, totally separate ones. And in this case, we can just see that these three affect different pairs of bodies. That means we can solve them in any order, or we can solve them even in parallel, and it's going to be exactly the same result. And when we're done, we won't have covered all the contexts. We cannot include this one, for instance, because it's already being operated on by the other blue ones over here. If we just tried to solve all of them at the same time, we would, since they operate on the same bodies, we would have a lot of data races. And would also be, even though we might get some result from that, it also it wouldn't be the same, it wouldn't be deterministic, it wouldn't be the same every time we run it, which is also a property that we want. So when we do that, we have those three, then we have 4 remaining points. What we do is to sweep over those 4, not considering the other that's already solved, and then we mark the ones that can be solved in parallel. Note that those red ones, they cannot be solved in parallel with the blue ones. We have to finish all the blue ones first, and then we can start on the red ones. And then we just do that over and over until we covered all the constraints. This is a very simplified case, of course. In a real scenario with maybe thousands of bodies and tens of thousands of constraints, that's going to be a pretty large number of constraints that goes into each color. And a typical number for that could be maybe 10, 11, 12 colors that's needed to cover almost all constraints. And usually there's a small remainder. We don't want too many colors. So if we have a very small number of colors left, we can just put them in a special bin and go over them sequentially. That's going to be, as we'll see later, faster than making a separate color for each. So we have that. And then when these are fed, when we're going to solve these and we're going to process these after splitting them up, we start with the first color, throw that at the thread pool, and solve all those constraints as parallel as we can. And then we're going to proceed to the next one. And then we do that 6 times because we wanted to do 6 iterations. And in between each color, when these threads have been working on it, before we can start the next one, we have to wait for all the threads to finish. So that's a full barrier sync across all the threads in the thread pool. And we're going to have to do that between every color in every iteration. And as I mentioned, the number of colors are usually 10, 11, 12. And then we have a few additional jobs every iteration for integration and other things. So we end up with close to or around 100 barriers per step, or per time that we execute the solver. And given that this is a game that wants to update at 60 frames per second, and we also have other things to do, we have a collision detection and rendering and whatnot, that gives us just a few milliseconds to complete that. And doing this amount of synchronization in such a short amount of time is something that synchronization primitives aren't very good at. So in order to measure how they perform, I put together this little test scene. It's a level exported from Teardown to the new engine. I spawned a lot of dynamic objects, and it's actually 5,000 of them. I made so that they are all active and simulated at all times. And they're all, or most of them, are in a big pile. So it's a tricky case for the physics engine to handle. And the machine I'm running this on is an Intel Core i9, 14th generation Raptor Lake 900F. I'm not sure what those numbers really mean, but it has 8 P cores, or performance cores, as they're called now, with hyperthreading, so 2 threads per core, and 16 efficiency cores, summing up to a total of 32 threads. Now, whether we should count the hyperthreads or not could be discussed, but there are actually 24 actual cores in the machine. And as a baseline, if we run this single-threadedly, we get the number here, 82 milliseconds for the whole scene update, which is obviously not anywhere near real time. But the number we're going to look at throughout the presentation is actually one iteration of the solver marked here. So the thing that we do 6 times, I take an average of that, and that's the number I look at, because that's the thing we're trying to parallelize. So it makes sense to measure only that, right? And if I start out with a traditional, or what I call a traditional thread pool, it's actually very close to the implementation that runs in the current Teardown, or Teardown the game as it is today. It uses just standard synchronization primitives. So it has a shared task queue that fills up every time there's a job coming in. There are multiple workers pulling jobs from this task queue using a standard mutex. And then there are a couple of condition variables. One for if it happens so that the main thread has to wait for the threads to finish. The main thread also pulls tasks off the queue, but sometimes it finishes. There's no more tasks to take, but it has to wait for the threads to finish. It sleeps on this condition variable. And the same thing when the workers run out of work, and there's no more tasks to be done. They sleep on another condition until the main thread says, here's a new job. Then they can start again. And it looks like this. And you can already see this is kind of this looks a bit weird, right? We have very dense profile on the left and a very sparse on the right. And this kind of coincides with what we said before, collision detection on the left, very easy to parallelize, no data dependencies. Solver on the right, very hard to parallelize, lots of synchronization. So if we just measure the time there, we're at 17 times better than the single thread performance on the collision detection, which is really good, I would say, given that we have, I don't know how much you know about performance and efficiency cores. I'm not a hardware person, so I'm not the one to tell you exactly how it works. But the efficiency cores, from what I've come to understand, there are 4 cores in a cluster. They share an L2 cache, and they also have a clock speed that is lower than the performance core. And that in total makes them run at roughly half the speed of a performance core, from what I come to understand. And since we have 16 of them and 8 performance cores, we should get around 16, and 17 is, so that must be pretty good, right? If we look at the solver, we're at 1.4. That is like objectively terrible for having 31 threads on a problem. So I reran this with different numbers of threads, just to see what happens. And what's going on, it's a little bit hard to explain, but if I run at 8 threads, I should have had the graph. I didn't actually do all the numbers because it's a lot of manual work. But I tried it, and the one that runs fastest is the one with 8 threads. Now we can observe something interesting here, and that's the collision detection, which parallelizes really well. It sits at 7.6x, the single thread performance, expected because it's very close to the theoretical maximum of 8. Whereas the solver, which was with 31 threads, was at 1.4, is now at 4.7. So one part of the code is slower, another part of code is faster. That's kind of hard to work with, right? So in total, if we just look at the scene update, which is 20.5 in this one, it's 13.3 in this one. So in total, measuring the whole frame time, this one is actually faster. It's faster to run just 8 threads than 31. And the reason I chose 31, maybe I should mention, is that when you have a high thread count like this, I usually leave 1 for the operating system and background tasks. I found that to be good practice, just so you don't get hiccups. But anyway, how should we tackle this? Should we just, and why is it 8? 8, I think, is because we have 8 performance cores. That would make sense. But what should we do about it? And if we go back and look at this one and zoom in on one iteration, that should be able to give us some hints. And then we can notice 2 things. One is that in between, so these are the different high-level jobs, these like vertical green fuzzy bars. In between these jobs, there's a lot of just black space where none of the threads are doing anything. Also not the main thread, which is kind of weird because the whole computer is just sitting there for almost 100 microseconds doing nothing. And the other thing we can observe is that even when a worker thread is running, it's a lot of gaps in between actually processing tasks. And that's likely because there's a lot of contention. We have a single shared task queue and a lot of workers trying to pull from the same queue. So we're going to have a contention from all the threads trying to access the same resource. So I want us to think about these 2 things as 2 separate problems, even though they're probably related. So one, to try and alleviate this, I rewrote the job system from using standard synchronization primitives to using mostly lockless programming and atomics. I don't know, how many in here have used or are familiar with lockless programming? So that's more than half. Great. It's a way to spin on atomic variables to wait for something instead of using like an operating system primitive. The operating system primitives actually also use that a little bit. They spin a little bit in user space, usually before actually doing a task switch and going into kernel. But that's true for mutex, but from what I come to understand, that is not true for a condition variable. So, and it's also hard to know exactly because it's not really exposed what they do. So we have an atomic spin lock that spins, waiting. So when there is congestion pulling these tasks, the atomic spin lock will just sit there and go, is it available? Is it available? Is it available? Until it becomes available, and then it's immediately going to return. So there won't ever be a task switch or like the operating system blocking that thread or anything. We also have an atomic counter for completed tasks, so that if the main thread is the first one to finish, it's not going to sleep on a condition variable anymore. It's also going to sleep on this atomic, waiting for the number of completed tasks to be all the tasks. And in this version, I still have the condition variable for the workers, because we don't want to spin all the threads in the machine forever, because that's going to consume a lot of energy. The computer is going to be very loud, it's going to be very warm, and it's also not a very nice thing to do towards other programs. We might get punished by the Windows scheduler for doing that, so we don't want to overuse this opportunity to spin too much. But let's look at what this looks like. So on the left side, collision detection is roughly the same. I think that is within the error margin. Service is probably the same, which is expected. It was already fast before. It's not going to be magically much faster if it's already efficient. And the parallel solve on the right side is now at 3.8 times faster than single-threaded. So we're a bit closer to the 8-thread version. Not quite as good as the 8-thread version with the previous one, but much better than the 1.4 that we had before. And if we look at the scene update 10, that's actually faster. So by using lockless, we could make the whole frame time now running faster with 31 threads as compared to 8 threads that we had before. So by using, we actually get a benefit from using the whole machine, so to say. And if we then zoom in again, it now looks like this. And it's worth mentioning here that this distance here is now 880 microseconds, whereas in the previous slide, it was 2,200 microseconds. So even though it looks like it's approximately the same black gap in between jobs, it's actually much faster because it just scaled up. But we can see that once the threads actually start working on something, they're actually quite efficient. They're almost not noticeable, these little black things where they try to get the next tasks. So we solved one problem, and we made one problem better, but it still looks like something is a little bit off. They're doing more waiting than working still. And I think the solution here is probably obvious to everyone, since we still have that last condition variable in there that we don't want to remove, because the computer, we don't want to waste, or waste all that energy having it spinning all the time. What we could do is to have two versions of the thread pool. One that spins indefinitely, even when the job is finished. You can just spin from here to there. But we just want to do that while we're in the solver, because we know in the solver that when we finish the job here, all the threads will hang on that condition variable, and then on the main thread, 5 microseconds later, it's going to say, okay, time to wake up, everyone. So then they kind of make this switch, like go to sleep, wake up, go to sleep, wake up, which is very inefficient. But before we look at that, I just want to make mention an observation that I made. And I'm not a hardware person, so I'm not. I don't know what I'm talking about on this one, but I just want to mention it because I couldn't unsee it once I saw it. When I've been staring at these graphs, I see that it's usually when the main thread says start working, there are a number of threads that start early, and then there are kind of a gradual period before everyone started. And the time it takes from the main thread says start until all of them started is roughly 30 milliseconds or 30 microseconds. And if we just look at these that start early, you can see that it's 1, 2, 3, 4, 5, 6, 7. These are a little hard to measure because they're so small. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You start to see a pattern. It's like almost always it's 7 threads that start early, and then the rest come way later. And my theory is that those are the performance cores, and that's also why the 8-core version is faster. I cannot really back this up, but that's just my theory. But now let's try to remove that last condition variable. So the only modification I made was to have a Boolean on the whole thread pool that basically says if we are in this elevated performance mode or low latency mode or spin mode, as I call it. If we are, we just spin on an atomic while waiting for the next job, or that Boolean to go to the normal state, then we also break that spin. And looking at the results, we're now up to 9.1x on the solver side. Collision detection also went a little bit better, up to 19, but I think that could be, it could also be just random noise, I'm not sure. And overall, we're down to 6.6 milliseconds for the whole simulation time, from 82. So I don't know what that would be. It's like a total of maybe 12, 13x. And if we zoom in, as we always do, on one iteration, we can now see that this is starting to look pretty reasonable. It's actually doing what it's told. So if the main thread says, can you start this batch? All the threads are pretty quick. They start at roughly the same time. Also, another reminder that this is, again, scaled up, just so you can see it better. It's now 330 microseconds across. So the time it takes to start all the threads here, it went from 30 microseconds in the previous one down to just, you can't really see the legend here, but it's approximately 2 microseconds in this version. And once the last worker stops working, the main thread immediately continues without sleeping and starts the next one. And then it just goes in sync with the workers. The only real gap we have is this one. But that's the serial part. That's the special bin of constraints that didn't get colored that we solve in sequence. It's been there in all the graphs, but it's been so small that we didn't see it. And now we can finally see it. So I see that as a good thing. now the whole graph finally makes sense. So as I mentioned a couple of times now, the scale of this is different in all the slides. And I thought it would be interesting to just lay them out and see them side by side. So I just scaled the image, actually, to have the same time, so to speak. And now it gets pretty obvious. It's the same amount of, it should be the same amount of green in all these graphs. It's just the amount of black gaps where the threads are waiting that's different. So that's that. And I also actually put them in a diagram like this, where I grouped them a little differently. I have the single-threaded on the left. I did these 3 methods, the synchronization primitives, the lockless or partially lockless in the blue, and then this spinning mode lockless on the right. And then I measured the whole things with 8 threads and with 31 threads to compare. And as we can see with the sync primitives, much faster with 8 threads. With the lockless, still faster with 8 threads, but it's like at least approaching the same range. And if we just spin in between jobs, the 31 threads outperforms the 8-thread one by quite far. This, by the way, is just for the solver. If we would have included the collision detection also, that would be an even more dramatic difference because of the collision detection. I redid the same thing with AMD. I have a Ryzen 7 laptop that has 8 Zen 4 cores, and it uses AMD's version of hyperthreading called simultaneous multithreading. It's basically the same thing. So 16 hardware threads. So instead of 31, I'm using 15 threads on the right side. And I thought it was quite interesting that the overall trend here, or the overall how they differentiate, is roughly the same, even though it's a completely different architecture. So with the sync primitives, 8 is faster than 15. With lockless, about the same. And with green, we do get a benefit from using also the hyperthreads, or these SMT threads. I do have a couple more slides, if we have time. Just some closing notes on having access to a low latency thread pool like this has affected the way I think about parallel programming a little bit, which I thought would be interesting to share at a conference like this. When you have regular task systems or job systems, thread pools, whatever you call them, the most common way to interface with that, to my knowledge, is to have some kind of task that you define. And it could look, if you use C++, it could be like a base class, a task, and then you override a run function, a run method, and then some state that this task operates on. If you use C, it could be a function pointer and a struct. It could look a little differently. And then at some place in the code, you would build a task graph. So you would assemble these tasks. You would allocate memory for them, put them somewhere, copy the state, add them to the scheduler, insert these barriers, and sometimes you have dependencies between the tasks instead of manually setting the barriers, and then all that happens implicitly. And then once you built that, you execute the whole thing, and then that runs, and then implicitly just calls all these callbacks in the right order from different threads, and just magically it resolves this graph. I never, ever liked this style of programming. I think it's horrible. I think it's very different from how I normally think about programming. If I sit down and write like a prototype for something, I would never dream of using this paradigm for doing it. I would just write it like from top to bottom, like sequential code. And usually this is necessary because you want these dependencies kind of stated in that graph. But what I noticed from my own behavior is that when having access to a low latency thread pool like that, I've started to use a very old concept in parallel programming much more, called the parallel for, which is very simple. All it does, it loops over a number of things, and it does them in parallel. That's all it does. And then it does, then it waits for all of them to finish before it proceeds. So all the measurements you saw in the previous slides were actually done in this way. It's just, it's not exactly this code, it's simplified a little bit, but you have this outer loop. First, we prepare the graph coloring to compute these, what should be solved together. And then we make an outer for loop of 6 iterations. And for each iteration, we go through all the colors, and then we just solve all of them in parallel. Do that for all the colors. Then we solve these sequential batch only on the main thread. And then we do another parallel piece of work for the static contacts. And it's just very easy. It's very similar to the intuitive prototype version of this algorithm, right? And the only thing that I really needed to do to make this run efficiently was to set the thread pool in this elevated state. And I do that with a little scope variable. So when it enters that, it elevates the state. And if there's something to do on the main thread, it's also beneficial to do that when you enter the function. So in this case, I tell the workers to go to this elevated state, and then I know it's going to take 30, 40 microseconds for that before all the threads are ready and alert. So I have some time to do the graph coloring while waiting for that. And then you can just work with the worker threads, let the worker threads and the main thread work in a much more synchronized fashion. If you don't have to pay the price of this latency, that's proved, for me at least, to be a viable way to work with parallel programming. Saves a lot of boilerplate code. You don't have to allocate memory for these tasks. You don't have to copy the state. You don't have to come up with names for these tasks and all that tedious work that is not so pleasant. So for me, that has been quite eye-opening, or as like a new way that's, or an old new way that's viable again. So conclusion, I think the takeaway here is not to do exactly what I did. I think the takeaway here should be that all these graphs we've looked at, having access to looking at the way the threads communicate in a visual way, I think for me has been very, very useful. And I don't think I would have come to these conclusions without seeing all these gaps in the timelines and how the threads collaborate. So I can highly recommend, if you're not visualizing your profiling data in that way, or collecting the profiling data that makes it possible, I would highly recommend doing that. And then depending on your workload, you may want to do something similar or not do it, or something completely different. But then at least you're making an informed decision. Yeah, for me, changing the way synchronizing threads made a huge difference in performance. And that's the end of the talk. I just want to leave this with a little physics movie. And if you have any questions or you want to reach out, you can see my contact information down there. And thank you for listening. Thank you.
So how many objects are we seeing?
Could be around 10,000, maybe. I don't know. Maybe between 5 and 10,000, maybe.
So how do you think about the batch size in the parallel 4? So you don't want to assign just a single constraint to as the unit of the task.
Yeah, it's a good question.
And then you have static versus dynamic scheduling.
Yeah, it's a good question. It's a little. You have to again measure, I think, to see what's a good batch size. I think it's 32 in my case. I tend to. This got very specific very fast, but the number of tasks I generate, I think, is 4 times. Could be 6 times. I'm not entirely sure, but somewhere around that range, the number of workers. So I have a good number of tasks to choose from to not have so much static scheduling.
So, big round of applause for Dennis one more time.
Thank you. Thank you. Is this still on? Okay. Okay.
So my first question is regarding the profiler you mentioned. You needed to build this from scratch, right? Is this your work that you had like library that you actually could use? What was
This
story?
was my own custom profiler, yes. I have a history with profilers, so I like them, I use them a lot. But there is a really good free one called Tracy that you could use if you don't want to write your own. It's actually not that much work to write your own. You just have to be very careful how you measure performance, because you can't, if you want to measure performance of something lockless, you can't have a mutex in your profiler, because that can mess up the whole timeline. So it has to be a lockless profiler also. But as long as you have that, collecting the data is really simple. You just record all the, I just call query performance counter and note the results. And then at the end of the frame, or when I visualize this, I kind of sort out all that and see which thing should go where, and so it doesn't affect the thing while measuring too much.
Awesome. So I have a question. This was all CPU stuff,
Yes.
right? And everybody's crazy about GPUs in terms of rendering. So does it make sense to offload some of that work during the physics, either the collision detection or the actual solving part, to GPU and use the resources there?
You certainly can, and it has been done. But I'm not a big fan of the idea for two reasons, and one being that the GPU is pretty busy doing rendering. You probably want it to focus on that. And the other one being the latency. Or, well, if you want to put physics on the GPU, you either want very low latency and high bandwidth between the CPU and GPU and have them work in sync, so the CPU can say start crunching physics, or just the solver or whatever is on the GPU, and then get the result back. But it's going to be rather inefficient because the GPU is going to be busy rendering stuff, so it's not available just for random requests. Or you put all of it on the GPU and just tie it into the physics or the graphics.
Have you tried that?
No, because the result of the physics is also very tied to gameplay. So when you want the result of the physics on the CPU, and you want it usually immediately after you're done with it. And in our case, for Teardown, it's not really possible, because the physics could also result in things breaking, and you want to create new objects, and putting all of that on the GPU, you're going to end up with pretty much the whole game on the GPU, and that would be a nightmare.
Okay. I sometimes talk to game developers, and when we talk about physics, they are always complaining. And you spent your entire life on physics and physics engines. And my question is this the skill issue on the developer side? Or is this like inherently complex? How can a person get into physics and learn how to do it properly?
I think you just answered the first question with the second part. Like there aren't really a whole lot of good resources for learning physics. There used to be the bullet forums, but there's not that much activity these days. But like 10, 15 years ago, that was a very active forum where people helped each other, and we haven't seen much of that lately. So I don't know at this point. It's not particularly complicated compared to anything else in game development, I think. But it's maybe doesn't have the same mass appeal as graphics. It would be hard to make like a shader toy for physics. I don't really know what that would look like. So getting people into it takes maybe a little bit more of an investment before it starts working. That could be one.
Right. So from your talk, we started with like mutex and synchronizing threads, and then we ended up on the spinning lockless implementation. Does this implementation have some sort of downsides? Like, are there situations where it shouldn't go this way because it wouldn't work, or is it just always better?
Well, the most obvious downside is that it can consume more power. It will require more energy, but I think that is only true in some situations, given how much shorter time the solver runs. I'm not convinced that the total amount of power would actually be less if it went to sleep and woke up like 100 times instead. But spinning on atomics like this is not something that is generally recommended. If you look at the whole system, like if you're running the game and a lot of other things, that will probably not work very well because the game is going to, if you get like a context switch in the middle of the solver while a lot of threads are waiting, spinning, then they're going to keep spinning until, if we say for some reason the main thread would be swapped out while the workers are spinning, waiting for more work, they would spin a whole time slice before the main thread gets swapped back in. I think in practice though, I don't really see how or why that would happen. But if you run a lot of things on the machine, it's gonna start to become really inefficient.
All right, I think we have time for one question from the audience.
We have okay time.
Okay time?
When we need to go.
All right, so let's open up the floor for questions from the audience. Who would like to ask the question? Yes?
So this is more of a general physics programming question. So
Sure.
if you're applying the solver to multiple bodies, I would imagine that you start at a different point in the chain when you're applying impulses that it could potentially lead to a slightly different solution, right? Like it's order dependent. So what kind of general conventions are there for deciding what order to start in? Because I would imagine those would lead to slightly different results.
Yeah, that's entirely correct. That's also one of the reasons we want to have determinism. It's not only for networking purposes or anything, it's because of stability. If we solve the constraints in the same order every time, we're gonna have a result that is slowly converging to the correct solution. Whereas if we solve them in random order every time, we're gonna end up with disturbances that it can't compensate for appropriately. So we're gonna end up with jittering. And there's also, I don't know if that was the question you were asking, there's also been, in the past, there's been experimentation with reordering constraints. Say you have a stack of objects, if you want to solve it from bottom to top order and things like that in order to increase stability for stacking. That's also been done. But I would say that that's a minor thing compared to the general stability.
If I could just clarify the question.
Yeah.
The question was like, what kind of conventions are there for deciding what order to go in, if that makes sense? Like, is there particular conventions that for deciding what order to actually use?
Yeah, apart from these, if for stacking, for instance, if you want to solve from top to bottom, that's generally preferable. But I would say in practice, what I do and what I know other physics programmers also do is that there's some kind of consensus that it doesn't matter that much which order you solve it, as long as it's consistent. So what I do, I just do a radix sort. So I sort them per body, and it's incredibly fast. And I do it actually on the main thread before the solver starts. But it's at least with 32 threads, it doesn't really take up that much time on the profiler.
All right. Next question.
You mentioned there was potentially some sort of penalty from the operating system if you don't go to sleep. Is that a particular thing on particular operating systems?
It's just something I observed on Windows. I don't know if it's there's some just certain cases or if it's always. But if I make an error so that they're always spinning, I notice that the operating system. I don't know if the punishment is intentional because this process is doing something bad, or if it is just the time slicing that makes it get swapped out more often in the middle of something. It could be either of those, I guess.
John?
Did you ever experiment with work stealing? Because you only have one work queue, right?
Yeah. It's an excellent question. It's actually one I should have put on a slide for future work, because work stealing is generally a better algorithm where you don't have just one single queue of tasks, but you have one task queue per worker, and then they steal work from each other in the case they run out. So you have like a static batching that turns into dynamic batching once all the work is done, so to speak. And I want to try it. I haven't tried it yet. I also noticed in the profiler that these black gaps in between jobs with a lockless are so small that the potential speed up is pretty small, I think, in my case at least.
Holger?
Do you think that there is a way to overlap these iterations? Because you will be touching stuff that's not going to change during the previous iteration?
If that was the case, they would have ended up in the previous color.
You know, like the iterations, like when you're done with some of the...
Oh, I see. Potentially, there might be some opportunity for optimization in the overlap going from one iteration to the next, but it would... My intuition is that would be pretty small, but it's a good idea. Should maybe look into it.
Sam?
Yes, I guess. So I wonder, you describe that on the main thread you do things that I presume touch all n of the contact points. It sounded like. So is it? I'm trying to get an idea for how much more expensive the solve, each constraint solve, is compared to just iterating like, because you, for example, said you sort them, right?
Right. Are you talking about a memory? Just
why is it expensive? Why can you go over all n contact points on the main thread but you can't solve? Like, how much more expensive?
Yeah, it's a lot of computations to solve each constraint, so that there's a significant amount of operations that needs to be carried out. So it's yeah, but you're right that going over and touching the memory on the main thread for everyone, that could, if you have a lot of constraints, that could potentially be a bit expensive. The total memory for all the constraints, even if you have 10,000, they're still all going to fit, maybe not in the L2 cache, but at least in the L3 cache. So it's not going to be a major bottleneck when it comes to memory.
And just a quick follow-up then.
Mm-hmm.
Are there variations in how complex a solver could be? Like, for example, is teardown solver a lot more complicated than what somebody else might do? Or
I don't think so. The solvers, at least from what I know, are relatively similar as long as they follow this projected Gauss-Seidel or sequential impulse. They could be implemented a little differently. The new one that we saw here is actually a bit different from the one in teardown on in a number of ways. But it's the differences are rather small, I think.
Ryan?
So I'm not a good physics programmer, so let me know if this doesn't make any sense. But with the sequence of iterations, you have, like, let's just say you have blue color, red color, green color, and then the second iteration you do blue, green, red, whatever order I said. You do that many subsequent times. Is there a dependency between, like, blue number 2 and red number 1, if that makes sense? So, like, could you do all the blues first and all the reds and all the greens, or can you not slice it that way?
No, you have to solve all the colors in one iteration before you can start the next one. That's it's almost like the iteration is just a continuation of this sequential thing. So you have to finish all of them before you can start the next one.
The iteration is just basically just to make the step small enough so that you have fine enough correction, right? That's the only reason we do iteration.
The reason there are iterations in the solver is to increase accuracy, because it converges towards the solution. The more iterations we take, the closer we get to the solution.
And how did it happen that it's exactly 6? How did you
It's
find
just
the
experimentation, like what you need for the game.
Okay. Will this be
it's-
stable from game to game, or
From what I know, most games use 4 or 8. There are probably some games using a bit more, some a bit less. Some physics engines let you set that per body. So if you have a simulation island with all have a low iteration count, then it's not going to spend so much resources simulating that island. So it can look a little different, but it's a performance quality trade-off.
all right, Taha?
Yeah, so I have a question. This is more general physics engine optimization, and that's, do you do a thing that, for example, you measure, for example, you see if an object is really far from the player camera, you do less physics iterations on it? Or if you see that the object is really stressing the physics engine, you just like silently try to do less iterations on it?
Usually, no. I don't do that, at least. I don't know if someone else is doing it. I think it's pretty uncommon, because generally, if you have things that are scrambling around somewhere trying to settle, if you turn down the iteration count, the simulation quality is going to go down, which means they're going to be more shaky and jittery, which it's going to keep them alive for a longer time. So when something settles, you can take them out of the simulation. So at a larger scale, you might actually waste time by doing that.
Are there yes SQ?
Have you thought about keep storing in the objects if they are solved, so that you say the first color is one value, the second, and then you can check, hey, I'm in the second wave, have both of these contacts been solved in the previous, and therefore you don't have gaps where you have to sort of collect everything?
Do you mean for each iteration you would do this to see if they need further solving, or I'm not sure.
Yeah, so if you have a contact in the, what would you say, the second color, right?
Mm-hmm.
And that contact can only be solved when the first iteration is done. But it doesn't have, the whole first iteration doesn't have to be done. Only those two objects.
I see what you mean. Yeah. No, I have not experimented with that. I think that would be a very complicated thing to implement unless you want to do it, because then you want to have atomics for that checking. It's an interesting idea. I think it would be a lot of locking and quite expensive, but it could be worth checking.
All right.
Dumb question. If there are no good resources, when can we get your book?
I don't think I'm not planning on writing a book, but I agree that there should be more physics resources. There's been a couple of initiatives to do more. The best I know is Aaron Caro's blog. It's very good, and also if you're interested in the solver specifically, he released just last year a project called Solver 2D. It's on the same GitHub account as Box2D. That is a simplified implementation of, 10, 11 different solvers. And the code is very easy to read. It's like written just to compare the solvers qualitatively. So it's not written for performance. And that's a good resource if you want to learn what different solvers do.
But besides Erin Kato's blog, there is also voxagon.se blog by Dennis himself. So while we wait for his book, you can go to this website, voxagon.se, it's Swedish domain, I presume. And Dennis has amazing blog posts, very detailed, very nicely written. You can go a lot, you can learn a lot from these blogs. So go check out voxagon.se.
Thank you. Thank you.
Masha.
Yeah, so you said that bad things would happen if you have more than 10 colors around like that. Is it the same as you did with sequences, with trial and error iterations? Or like there is some dependence on the number of objects, like how to determine the number of colors?
Yeah, the reason I want to keep the number of colors, I want to cap the number of colors is to not have, because each new color requires a full synchronization, so there's going to be some time lost, and if you don't have enough work in each color, it's just going to be waste at that point. So it's a little bit of trial and error to find that sweet spot. I think in my code, I actually have 16 as the cap, but it usually never reaches that. It's finished by the time it gets to 10, 11, 12. And then I have another cap at how, when there are only fewer than a certain number of constraints left, I just put them in this overflow sequential bin. And I think that number is maybe 32 or something that can be solved very efficiently in sequence. I just don't bother doing any labeling for. I just quickly want to proceed to the actual solver.
Yes.
How did using SIMD instructions factor into the optimization? For example, was this important, or was having enough threads?
It's a good question. If you go to Aaron's blog, he's been experimenting with that. So he's actually doing graph coloring also for the purpose of SIMD. So he solves parallel on a bunch of different threads, and on each thread he solves constraints with graph coloring also on different lanes with SIMD, which is pretty cool. The new Box 2D is amazingly fast.
All right, thank you so much. This was so many questions. A round of applause. Dennis Gustafsson,
Thank you.
Tuxedo Lab.
Thank you.